I'm going to talk about some project I've been doing with Matthew Baring and Zoroar Wadiyasingh for a while. As Dong already talked about, magnetars have persistent emission. Most of them have a persistent spectrum, which is made up of several components. At the low energies, it's a thermal component, or one or two thermal components, being about a half a keV temperature. And then above about 10 to 20 keV, you have this hard, very hard component coming in that goes up to at least, I guess, about 100 to 200 keV, maybe more, but it has to at least turn over at some point around an MeV. And many of these magnetars have these components. There may be a trend going from young to old in hardness and level of these components, but just about all of them seem to have this. And this is a collection of magnetar hard components with the COMTEL limits and possible amigo sensitivity. If that kind of MEV telescope ever gets flown, it can begin to see where this cutoff is. But we are going to concentrate, we're concentrating on that component to begin with as being caused by accelerated electrons due to field twists. This is basically ideas that have been going around for a while, starting with Belovaradov and Thompson, and then Belovaradov 2013. This is a figure from that paper where he envisioned some injection of electrons that then Compton scatter on these half keV thermal photons. And if you have a twist, say, on a dipole, general dipole field, you can have twists caused by crustal motions. And the twisted magnetic field induces currents, and then these currents, this twist decays, and the electric field can accelerate particles. And it basically need particles to sustain the current. And the question is, do you have enough particles to sustain it or not? And I guess the idea is that you have the initial accelerated particles find themselves in the cyclotron resonance in their rest frame. And then there's a huge cross-section. They can resonantly Compton scatter. And this resonance is right when you have gammas of about 10 to the 3 in magnetar fields. Well, there's been a number of studies of twisted fields in magnetars, and this paper from Palfrey studied force-free twisted fields. Basically, this is an MHD study. Also, Chen and Belovaradov did a PIC simulation of a magnetar twisted field, and they concluded that to sustain the twists, you definitely need some kind of pair production. So what we're going to do in the study is create the photons from resonant inverse Compton scattering on electrons on closed field loops, closed dipole field loops. We're assuming that there's some small or some kind of twist on these loops that accelerates the particles initially, but otherwise the field is dipole in our study. So these particles, they start out from one of the foot points, and we're going to start them at the southern pole and go up towards the northern pole. And at some point along this trajectory, they're going to start emitting resonant inverse Compton photons, which at the highest energies are very, very beamed along the magnetic field. So if you're an observer wanting to see this emission, you can see the emission, say, at 60 degrees, primarily from electrons at this point, where the emission is then along the local B field. At lower fields, this emission spreads out a bit, but we're going to assume, for simplicity, because we're really dealing with the highest energies that get attenuated, that all of the emission is beamed right along the magnetic field. So it's important to use QED cross-sections for all of these processes. in magnetar fields. And this is an example of if you have relativistic particles, you basically, in their rest frame, they see most of the photons coming right at them along the field, if they're moving along the field. So you only have the fundamental resonance. But this resonance now, it's for the very high field strengths, and this is the cyclotron resonance, cyclotron, or Thomson limit the Thomson limit is the blue line. And then you have the QED, exact QED cross-section in solid. And you can see that as the field increases, because you have electron recoil and you're approaching Klein-Nishina limit, that really reduces this cross-section. So you have to make sure you use the QED cross-section, which we do. So this is the result of a paper that Zorower wrote in 2018. He calculated resonant Compton upscattered spectra at various different angles, and it was basically, it's very angle dependent because where you see the particles depends on whether or not they get into the resonance at all. So these are different angles and different colors, and you can also see the Thomson limit spectrum is going it's violating conservation of energy basically. So you're overestimating all of this radiation unless you use the QED cross sections. And you can see there's polarization dependence, especially at the highest tip of the spectrum, and it's in the perpendicular mode. And this is another example from his paper where you basically have a little bit higher energies. You have more resonance conditions possible, so more angles now are in the resonance at the highest energies. So if we want to look at pair cascades, it really depends a lot on what field you're in, what the cascades look like. In low fields, which are basically kind of pulsar fields, around pulsar fields, you have a very extensive cascade because both polarization modes can pair produce. And then the pairs are produced in very high Landau states, so they produce synchrotron photons, and those synchrotron photons produce more pairs, and you can have many generations and lots of multiplicity. But above about 1/10 of B critical, you have pairs starting to be produced in the ground state. So parallel mode photons produce pairs only in 2 pairs in the ground Landau state. But for perpendicular mode, you have to produce one of the pair in an excited state, first excited state, and then that pair can synchrotron radiate and produce another pair. And you can have a little bit more cascading, but it does, kind of put a little bit of damper on the cascade. But then about half B critical, photon splitting comes in and becomes more important than pair production. And so then it depends on which splitting modes are allowed. And there are 3 kinematically allowed splitting modes in the non-dispersive. But in the non-dispersive limit, we don't know, whether there's just this one splitting mode or 3 splitting modes. In the low dispersion limit, we think there's only this one. Perp goes to parallel-parallel. But we don't know, and magnetars could be in the dispersive limit. So we could have 3 modes of splitting. And then it depends, because the parallel mode photons produce pairs, but the perpendicular mode photons produce 2 parallel mode photons, which just produce pairs in the ground state. So then you don't have much of a cascade. You don't have much synchrotron radiation. But you could have a whole splitting cascade. So it's a little unclear. We're going to assume only splitting in that one mode for now. And of course, Dong went over very nicely all the different processes. With pair production has a threshold, where photon splitting has no threshold. So you can actually have photon splitting below pair threshold. So that's important. Now, it's also important to treat synchrotron radiation in the quantum limit, because, of course, you can violate conservation of energy pretty easily in magnetar fields. And so we use this asymptotic formula for high field synchrotron radiation, which actually works pretty well. These are shown on the right here, and it even reproduces this tip of the spectrum where an electron wants to radiate all its energy in one photon. So this is what our pair cascade kind of looks like. At very, very near the neutron star, you have photon splitting dominating, and those split photons will produce some more photons. And it's possible that depending on where those are produced, you can produce some of these photons in excited states. Some of these pairs in excited states, which produce synchrotron photons. But actually then when you have parallel mode photons, you always pair produce. And those photons can be in low states or they can be in higher Landau states depending on what your field is. And so if you're going out along, say, one of these closed loops, which is defined by the maximum of the loop, in this case, that one would be 4 neutron star radii. It depends on where you are, and you can have low enough B fields at the top of the loop to produce full cascades, depending on your surface field. So the paper just went on the archive yesterday, so you can look that up. So as you're going along the loop, and this is going from the surface to the top of the loop, the loss rate of resonant inverse Compton scattering can be quite high, and it also varies a lot with radius. So if you have a gamma of 10 to the 3 particle and a B field of 10B critical, you're in the resonance right at the surface. So the loss rate's very high, and the particle starts to lose energy right away. But then as soon as it loses energy, it gets out of the resonance, and so then it stops losing energy for a while. It loses energy, very slowly. And then it gets into the resonance again near the top of the loop. So it's a complicated dynamics with some of these particles. When you have a higher surface field, you're not in the resonance at the surface. So you don't lose energy much until you get to the top of the loop, and then you start losing energy. So you can maintain the particle energy for longer. And you get to the top of the loop, of course, the B field is dropping. That's why you can get back in the resonance. So these are some spectra for the case of no resonant inverse Compton losses. Now you can have this situation if, for example, you have some kind of acceleration which is more extended and you can keep the particle at the same energy. It's not clear that that's going to be what happens. I think the resonant inverse Compton losses are too large, but anyway, I do this also to compare with Zoroar's previous results, and we compare pretty well with his results. It's a little, let's see, okay. So this is an example for gamma of 10 to the 3 in both polarization modes and a B of 10, B critical. And this is for different viewing angles. So what's shown here is in light lines are the unattenuated spectra, and the solid lines are attenuated spectra. So these spectra are attenuated by both pair production and photon splitting. And you can see that the energies are different, especially for the very high field strength. You can have the pair production attenuation is at higher energies because it has a threshold there. But the photon splitting is at lower energies. So you can have a range of 100% polarization in the parallel mode. And in this lower field strength, you only have photon splitting being important at very near the surface, which is this 120-degree viewing angle. As soon as you get up to a 90-degree viewing angle, you're at low enough field strength, so both modes pair produce. And then you have a reversal in this because the parallel mode actually has a lower threshold than the perpendicular mode. So you get this interesting reversal, and then you can get 100% polarization in the opposite direction. So, and this is now with energy losses. The same thing with energy losses. Okay, ooh, okay. And you can see that there's a big loss by the time you get to 30-degree viewing angle at the top of the loop. You've lost so much energy that you're not even being attenuated anymore. The photons are low enough energy that you basically just have a kinematic cutoff. And I have to go through this quickly, but this is the higher field strength. And you can see you don't lose as much energy as you go up to the top of the loop. So this is the spectra of the resonant inverse Compton that you saw. Well, this is with no energy losses, but the colors are the resonant inverse Compton. And then you have the cascade radiation. In purple colors, you have photon splitting, split photons. And the green colors are the synchrotron radiation from the pairs. And right away, you see that both the splitting and the synchrotron photons, they overwhelm the original resonant inverse Compton spectra, in this case, with no losses. Then, of course, you have interesting polarization characteristics, which I don't have time to go into all the details. Now, with inverse Compton losses, you still have synchrotron radiation. Which, and in some cases, splitting, which can overwhelm the original resonant inverse Compton spectra. And notice that in both of the cases, with and without losses, synchrotron radiation spectra are a lot softer. These inverse Compton spectra are too hard, really, to match the observed spectra, but this synchrotron spectra can actually match what you see a lot better. And this is just a case of a higher field strength. You have less synchrotron radiation, but more photon splitting. And that's expected because photon splitting pretty much is dominating almost through the whole loop. Now, these are some pair distributions. This is without losses and two different energies of the initial pair, but both 10 times B critical. And you can see that the pairs are mostly produced around the loop, but some of them are actually produced further out. It depends a lot on the mean free paths and, you know, a lot of the details of synchrotron radiation. And this is when you increase the loop size to a maximum radius of 6 neutron star radii, you get a lot more pairs and a lot more multiplicity. And this is still with no synchrotron losses. No resonant inverse Compton losses. And this is the case with losses, and you get a lot fewer pairs, but you still get enough pairs to produce enough synchrotron radiation to overwhelm the original resonant inverse Compton spectra. Okay, so this is the pair energy distributions with and without losses. And of course, this is no losses. You get much higher multiplicity. You can get 10 to the 4 or so pairs per primary. With losses, you get fewer pairs. And since we're ignoring resonant inverse Compton from the pairs at the moment, it's very justified for the loss case, but probably not quite for the no loss case. Now, I want to get to some observations, comparing with observations, and Dong already talked about this particular magnetar, which has very low, fairly low polarization at low energies, but the polarization increases much at the high energies as power law components come in. We get polarizations of 75 degrees maybe in some cases, which is quite high. And this is a paper which we recently published. We got observations, XV observations of this magnetar in outburst, and we see a similar thing. We see that the polarization is low at the lower energies and goes up to at least 50% at higher energies, and we fit this with power law 2 black bodies. And then this is XP plus new star data, and new star really traces this hard power law out. So we actually, by the time you get to 4 keV, you are in this power law kind of regime. And we think that this is, in this paper we show that some of our pair cascade synchrotron spectra match this high energy part very well. And this is right here. It's about 1.5 spectral index, and it also is pretty highly polarized. It's around 50% polarized. Okay, I'm just about done. And so it looks like what we may be seeing in this hard component is the pair synchrotron spectra, not resonant inverse Compton. Okay, so this is the summary. These resonant inverse Compton photons will initiate a pair cascade. I mean, it's hard to avoid. And they're attenuated above a few MeV, so we expect, the cutoff should be interesting to study with polarization. And the split photons and synchrotron are going to contribute a lot. They're going to basically overwhelm the original spectrum. And then we can get high degrees of polarization, as you just saw. And I guess I'll leave it there so I can.
Okay, thank you for this very interesting talk. So we have some time for questions and comments. I'm going to come to Chris first, and then over to Andre.
So the cross-section for gamma-gamma collisions is enhanced in the strong V field.
Yeah.
And there are lots of, few keV photons floating around. Before the photon can pair convert, is that an issue?
Yeah, so when you said the photon-photon cross-section is enhanced, I think it may be depressed a little bit. Well, it always is highest at threshold, right? But if you look at QED effects in the B field, it's a little bit depressed from vacuum because there's less phase space. But so it may not be as high.
When you're well above BQ, it's enhanced by a factor of overall normalization factor of B over BQ. Then there are kinematic effects, agreed.
Okay. Well, yeah, we can talk about that. But I've seen your papers, yes. So I know, what you were talking about.
Alex, do you have continuous particle acceleration in your cascade calculations? Or you just give a kick to primaries and then see how they emit photons?
Well, we do both. In fact, with the no resonant inverse Compton losses, we're assuming that there's some continuous particle acceleration to keep the particles at that energy.
Because I'm a bit surprised with high multiplicities you are getting. So just probably it's a result of that you have like a continuous.
It's a result of continuous acceleration to keep the particle at constant energy up to the top of the loop. And I mean that may or may not be realistic. It depends on how big your twist is. But if you do have losses, then yes, you have much lower multiplicity. It's like 100.
And okay, thank you. So just the last short question: how many generations do you have at most?
Yeah, I couldn't show all that table and everything, but we have like 4 or 5.
4 or 5. Okay.
Even 6 in some cases. Yeah.
Thanks.
Yeah, I forgot to mention this is a Monte Carlo code, which is why it's messy because some of the spectra are messy, but. And we have a recursive routine, so you can just call it as many times as you want to get as many generations as you want. So, yeah.
Are there further questions? I see Alex.
Thanks, Alex, for a really nice talk. I'm a little surprised by the fact that you pointed out that the low energy, like 10 to 100 keV, is dominated by the synchrotron. So my question is, does that only happen when you do not consider inverse Compton loss, or does it happen when you consider both the loss and without loss?
Well, it happens even with losses. Whoops. There we go. That's with losses. So, yeah, you can get synchrotron radiation near the top of the loop from different angles, but, it all depends. I mean, it's less synchrotron radiation than that case. That's with no losses. and this is with losses. So you can see it's less, but it still overwhelms the actual spectrum with the losses at that angle, at that viewing angle.
Do you consider what pitch angle do you assume, or do you just do you assume some pitch angle, or do you just follow the dynamics of the particle?
No, we follow the whole. We do full. Okay, so if the particle ends up in a Landau state 20 or less, we use quantum cyclotron formulae, where you have individual transitions, and we follow those individual transitions. So, pitch angle is what it's all the dynamic, all the kinematics is done. If it's above 20, we use the asymptotic formula, but we still make a Lorentz transformation to the kind of particle rest frame. And then, well, at least the perpendicular frame. And then we do the transition, and then we Lorentz transform back. So, yeah.
Yeah, it'd be great to talk to you afterwards, because we also have a poster over there. We did this calculation, but without the synchrotron loss, we kind of can get the observed hard spectrum just from the inverse Compton, the resonance inverse Compton. So it'd be great to chat, like, what our assumptions are and what difference.
I didn't actually have time to mention it, but Zoroar is working on another paper now where he doesn't do single loops of resonant inverse Compton. He does toroidal volumes. And if you do a big volume, for some very kind of low energies, it has to be kind of lower energy too, or you get cascading. For lower energies, you can actually start to approach the spectral index that's observed. But you need certain large volumes, But maybe you can do it with resonant inverse Compton as well.
Are there further? Yes.
That 2 Magnetar, so low energy, the 2 to 4 keV, even in your picture, it's entirely thermal, atmospheric, right? At low energy, 2 to 4 keV.
Yeah.
At high energy, in your case, is entirely coming from the pair synchrotron radiation.
We're just saying that above about 4 keV.
So the fact they are aligned.
Yeah, above about 4 is where the synchrotron should come in. Below that, and I didn't show that, would be dominated by the thermal spectrum.
Okay.
I mean, you can see where it is, and synchrotron is way below that.
At low energy, the emission is in the X mode, in your perpendicular mode, right?
Yeah.
So is that obvious in the?
So you would see X mode dominate. Yeah.
In the emission also.
In the emission for the synchrotron, right? Yeah, that's typically it's the perp mode that dominates. Yeah. Mm-hmm.
Okay, great. Then further questions, I suggest you find Alice during the break. So can we thank the speaker once again, and I will invite Thomas after.